And today I will be giving somewhat of an introduction to universal coalgebra. And the structure of this talk it won't be like one huge story. It will be a few different topics which are loosely connected, but which can also like stand on their own. So I hope everyone will be able to take something away from it. So this is kind of the roadmap that I have for today. So we're going to start with just like the basic stuff, the boring stuff that we need to get out of the way. Then we will be starting topic 1, which is final coalgebras and co-recursion. Topic 2 will be on behavioral equivalence by simulation, so notions of equivalence in coalgebra. And then finally, we will be doing some modal logic, which is kind of, I think, the most straightforward way of doing logic in universal coalgebra. So let's get going. What are coalgebras? Well, for so we start with the most general notion, which is that we have some endofunctor on a category C. And this is it's called B for behavior. And this will give us the possible behaviors of your coalgebras. And this is kind of like the type of the coalgebras that we're looking at. So you think, or maybe like the signature. And we pick some base object, which we think of as a set of states. And then a coalgebra is just a morphism from S to B of S. And of course, so I'm not asking if the B is like a comonad or anything. So this is not. So I'm not doing Eilenberg-Moore coalgebras here. This is just. So it's just a morphism. There's no properties, nothing at all. It's just a morphism from S to BS. Okay. And so this is, of course, it's also important to know like what are the morphisms of coalgebras, and it's kind of like the obvious thing, right? It's just some function f that makes this square commute. And again, like there's no other properties, there's no other structure, so this is just what a morphism is of coalgebras. Now, for the sake of simplicity, we're going to restrict ourselves to endofunctors in the category of sets, which means that S really is just a set of states. And this is because, well, for two reasons. One is that most examples that you may encounter in the wild are just based on the category of sets. And also the category of sets is particularly nice, and it just makes our lives easier. But lots of things in this talk are actually just, you can do them in general setting. You don't need the category of sets, but just for sake of simplicity, we're going to restrict ourselves to sets. Okay, so this is quite a general definition. Let's maybe look at some particular examples and get a feeling of how they work. This is an example which I find fun. It's black box machines, and there's actually several different kind of things that are called black box machines. But the ones that I'm looking at here, so they are like this big black box, and they have two buttons. They have an H button and a T button, and they have a small display that can flash as a color. In fact, when we press the H button, this display is going to give output and is going to give us a color. And pressing the H button doesn't have any other effects than reading it out. So if you press it again, we're going to get the same color. But of course, which color we get, it depends on the internal state of this black box. And when we press the T button, we're going to give this black box the command to go to the next state. And then after we've pressed that T button, like it may give us a different color. Of course, it may give us the same color. As, like we can't look in. look into its internal structure, so we can't really see what has happened, if anything has happened. But yeah, it may, like if we press the T button, it's going to go to the next state. Okay, so this is what to me is a black box machine, but actually, like what's a black box machine? What it really is a coalgebra. And why? How is it a coalgebra? Well, we have these two buttons, which are just functions, right? We have one button which takes the internal state and gives us back a color, and we have another button which takes the internal state and goes to the next one. So these are just functions, and we can of course put those together into a single function, which tells us that black box machines are just coalgebras for this particular functor. So on the left, it is the constant functor with value c, and on the right, it's just the identity. And now these are maybe very boring machines, and this may be a very boring functor, but actually it's not so boring. We'll meet them again later in the talk and see that they are actually can be somewhat interesting. But maybe a more immediately interesting example is that of deterministic automata. So if we look at the data of a deterministic automaton, we have some subset of accepting state, and we have a transition function. Of course, a subset of accepting a subset, I mean, we can just take as characteristic function, and that's equivalent. So we can think of this as just a function that tells us, is the state accepting yes or no? And on the other hand, like we can just take the A here and put it over there, and gives us like a function which gives us like the transition function at S, right? So it's still waiting for some element of the alphabet before you can go to the next state. And again, we can put these together and get a function from the set of states to this like composite, to this like object of composite states. And so a deterministic automaton is nothing more than a coalgebra for this functor. So it has the constant functor 2 times the identity functor to the power a. And in fact, you can also just make them non-deterministic by taking the power set instead of just the identity. Because then for any letter A, there are multiple different possible next states that you may go to, or possibly none at all. Okay, so these are some, I think these are nice examples for coalgebra, and they also reflect kind of the flavor that you know, there are possible, like you can get some observable behavior from it, but they also get some internal updating of states, which may depend on some non-determinism or some possible input. These kinds of things can all be represented using coalgebras. But just calling them coalgebras, I mean, I've rewritten some of the data to a particular form, but what have we gained by doing this is, I think, a justified question. So let me just give one nice example of what you can use coalgebras for, and what this coalgebraic perspective gives you. And to do that, I'm going to introduce some, maybe you could call it the data structure of streams. Because, well, what's a stream? A stream is just an infinite list, or maybe an infinite sequence. And so we fix beforehand some set of colors, and then we just, and a stream is just an infinite sequence of such colors. And let's just write streams for this set of streams. And what can you do with streams? I think there's many different things you can do with streams. I think the obvious, or let's not say the obvious ones, but the ones that are important for me right now are that you can take the head of the stream. You can just extract the first element, or you can take the tail of the stream, so you lop off the first element. And I mean, the typing of these two operations is that, right, you take a stream and you get a color, or you take a stream and you get a new stream. And so this gives the set of streams the structure of a black box machine, right, which we just saw. but in fact, it's a very particular black box machine because it has this nice property that if you take any black box machine, then there is a unique coalgebra morphism, like the behavior morphism, from S to streams. And so the streams are kind of the observable behavior of this black box machine, because what do you do? Well, you first press the H button so that you can read out the display. You go to the next state and you press the H button again, and you get the second element in your stream. And then you go to the next state, you press the H button again, and you get the third element. And this is like all you can do to figure out like what's the structure of this black box machine, because you cannot look inside at the internal structure. You can only use the data that you observe. And I mean, you can go through this. You can maybe like this is a nice exercise to say that right, if you have some state S, then this is a morphism of coalgebras, and it's the only such. Right. And so I want to put this a bit more categorically. I want to say that like the object of streams is final in the category of coalgebras for this functor. It's a final object. I mean, that's basically saying the same thing, but in categorical language. And another, so that was a final coalgebra. Another final coalgebra, which again is kind of interesting, is that of the language coalgebra. So we previously saw this functor for deterministic automata. And now, of course, an A language. So if we have some alphabet A, then an A language is just a set of words. And we can put these together into a set. And like as previously with the streams, we can give it the structure of a coalgebra by saying that a language is accepting if and only if it contains the empty word. And you can take transitions by, you know, just eating up an A if you're given it. And so this gives languages the structure of a deterministic automaton, or a coalgebra for this 2 times identity to the A functor. And in fact, it is final. It is a final coalgebra. And the unique and so if you are given some deterministic automaton, then the unique morphism is just taking the language accepted by the state. So if you map a state to the set of words that it accepts. And so again, so this final coalgebra is kind of, it contains the observable behavior. It contains all possible observable behaviors, really. And it's also, yeah, in this case, it may be something that we're interested in very much. So if we're given a state, like what is its image in the final coalgebra? Okay, so I've introduced these final coalgebras, and what we can use them for is to do co-recursion. And co-recursion is very much the opposite of recursion. It's recursion, but everything is backwards. And here's a fun example. So we're going to define an interleaving function from pairs of streams to streams. So if we have a stream A0, A1, A2, etc., and a stream B0, B1, B2, then we're going to map it to A0, B0, A1, B1, A2, B2, A3, B3, etc. And I claim that this is sort of a definition of this interleaving function. Because what I've said is that if you interleave and then take the head, well, that's just the first element of the first list that you take. And if you take the tail, so like we've interleaved, and then we take the tail, so we're just dropping this element, but that just means that we interleave this list with the tail of this list. So if you take the tail of this interleaving, then you just interleave S1 with the tail of S0. Okay, but why is this a definition? Right? That's maybe the important question, because these kind of look like properties that you want interleave to have, but I'm saying that it's a definition. Now, in fact, so I've made this to look kind of like Haskell, but it's not Haskell unless you define your own syntax for streams. There is a data type of streams. There's a library that provides it, but it doesn't use this syntax. It uses like different syntax. But why I chose this syntax is because I want to kind of make explicit the kind of duality between recursion and co-recursion. So if we think about recursion, so let's say we want to define a length function from lists over A, then we need to do two things. So we need to, I'd say, what does length do to the empty list? And what does it do to one element appended to a list? And now, so why is this a definition? Well, this is kind of because list is an inductive data type, or like it allows for a recursive data type. So it has these constructors, right? It has a nullary constructor of just the empty list and the unary constructor of adding an element to a list. And then in order to define a function out of lists, you need to say what it does, what your function does after you've taken one of your constructors. Now in streams being co-recursive, everything is backwards. So if you want to map into streams, you need to say what happens if you apply one of your co-constructors after doing your function. So it's really is just recursion in a mirror world. Anyway, that's kind of like the instruction, the analogy. But unfortunately, I have more things on this slide, so I'm going to clear these scribblings now. Okay, and now maybe if you want to be a bit more formal about it, is that what we're doing here implicitly is defining a coalgebra structure on the set of pairs of streams, where we say that H, so the readout of S0, S1 is just the head of S0, and the next state of S0, S1 is S1, the tail of S0. And then because streams was the final coalgebra, there is a unique coalgebra morphism from pairs of streams to streams. And so there's a unique function, which is a coalgebra morphism, and it being a coalgebra morphism tells us that exactly these two properties up here are satisfied. And so if you look at like the data type of streams, you actually see that this is how it works. So if you have some coalgebra structure on a type A, then you get a unique, then you can use that to define a function anyway. So that's co-recursion. Let me check how much time I still have. Okay. So next topics I wanted to cover was behavioral equivalence and bisimulation, because we've seen these final coalgebras just now, and we had these behavior functions which gave us the behavior of a state. And this was something that we might be interested in. And in fact, we may very well be interested in whether two of these states are equivalent, yes or no. And this is something that I want to be a bit more formal. So we say that two states in two coalgebras are behaviorally equivalent if they can be identified in some coalgebra. And now if you have access to a final coalgebra, then you can just always put the final coalgebra here and you get the same notion. But not all functors have a final coalgebra, so this is the more general definition. So if they just if they can be identified in any final coalgebra, sorry, in any coalgebra, then they are behaviorally equivalent. And this is, I mean, this is easily seen to be reflexive and symmetric. It's also, it turns out to be transitive, because you can take pushouts in the category of coalgebras. And in fact, on like the set of states, that's just an ordinary pushout. So if you go through the motions, then you see that if you identify two things, and then this one you identified with this thing, and then you take the pushout, then you identify these two things. Maybe just waving some hands around, and I hope it's convincing.
Ezra, can I interrupt you with a small question?
Yes.
So some people looking to various kinds of transition system are defining actually by simulation as a span, not as a co-span. Can you comment on that?
That's important, because this is not by simulation what I'm defining here.
Okay.
This is behavioral equivalence.
Okay.
Because this was actually my next topics, is that so co-spans are kind of somehow they're difficult to work with sometimes, at least. And especially if you think about it, you know, if you say, well, they're equivalent if they're identified in the final coalgebra, then you need to compute their behavior. But of course, if you really wanted to know whether two states are behaviorally equivalent, it's kind of going the wrong way around by if you want to just first compute their behavior and then check if they're equal. This is kind of putting the cart before the horse. So instead, what you can do is you can use spans. So we say that two states are bisimilar if there is a span that kind of unifies the two states, with a state that unifies the two states in a sort of more composite coalgebra. And so this gives you a notion of bisimilarity, but and in fact, so if you, like I said before, there are pushouts in this category, and so if you take the pushout of this span, then you get a co-span where these S and S prime are identified. So if two states are bisimilar, then they are definitely also behaviorally equivalent. Yes. So this is kind of a very abstract definition of bisimilarity. I want to massage it a bit into more relational flavor that may be more familiar to you. So let's take some relation between two sets of states, and we're assuming so these have some coalgebra structure on them. Then we can draw this diagram, and I mean this is a commutative diagram. Because what do we do? Well, if we have relation R, we can project on both coordinates and then take the coalgebra transitions. And then, of course, by definition of the product, right, this is a universal property, there's like a unique map here that makes it commute. Now, on the other hand, we also have, if we take B of R, like we have a map B of pi1 to BS and B of pi of the second projection to BS prime. And then again, we get a unique map to this product here. And now we would get a span if there is some map from R to BR such that this triangle commutes. Because then the projection morphisms will just be coalgebra morphisms. And so when does such a map exist? Well, here we do assume the axiom of choice. I'm very sorry, everyone. But such a map exists if the image of this map is contained in the image of this map. Because then whenever you, for every point here, you can pick a point here which is mapped to the same thing. And then by axiom of choice, you actually get a function here which such that this one factors through as this. So we get a span if the image of one of the maps is contained in the others. We can make this actually a bit more explicit. So this is equivalent to saying that if you have a pair of states which are related by R, then there is some P in BR such that B of the first projection gives you the unfolding of S, and B of the second projection gives you the unfolding of S prime. And in fact, so if you, for instance, do this for for automata or for cryptography frames or label transition systems, it turns out that this really just gives you the ordinary definition of bisimulation that you may have seen before. So maybe to spell it out, so if we have a relation from X to Y, then we can define the lifted relation as taking all possible sets, so all pairs of possible behaviors that are possible to identify by some P. And this lifts the relation R to a relation between Bx and By. And then a relation is bisimulation if we have that if S and S prime are related by R, then their unfoldings are related by the lifting of R. And as we've seen before, so by all of the preamble, we now know that by similar states, they are behaviorally equivalent. Sadly, not always the other way around. On some mild conditions on your functor, the other implication works, but not all functors, it doesn't work for all functors. But there's ways around it. You can tweak this definition of this relation lifting in order to maybe approximate behavioral equivalence a bit better, or maybe exactly. But anyway, we see that we are now so we can use bisimulation to compute an under approximation of behavioral equivalence. So if we can exhibit such a relation showing that two states are bisimilar, then we definitely know that they are behaviorally equivalent. But maybe not all behavioral equivalence can be captured in this way. Now I want to continue on to logic, which is going to approximate behavior equivalence from the other direction. And so I want to start by just reviewing just ordinary modal logic, but from a coalgebraic perspective. So a Kripke model is nothing more than a coalgebra for this functor. Because what does a coalgebra for this functor look like? Well, at every world, you get a set of proposition letters, which are marked true at this world, and you get a set of successors. And this is really just the data of a Kripke frame. Or a Kripke model, I should say. And now let's look at the semantics of the diamond. So diamond phi is true at the world if there is a successor at which phi is true. Okay. I now want to abstract away from this definition and look at the form that it has, because this form can then be generalized to a very general coalgebraic framework. So what's the form that it has? It looks like sigma of W, so the set of successors, has some property which depends in some way on the formula phi. And so we don't really care about W anymore. We only care about the unfolding of W. Right? If two states have the same unfolding, then they must agree on diamond phi, even if they are distinct. Secondly, this property, because the property was that some successor satisfies phi, it doesn't depend on all of the internal structure of this formula. It only depends on its extension, which is at which states is it true. Okay. So this is kind of like the form of the semantics for diamond. In fact, I want to now maybe make this a bit more concrete, saying that, well, I have this word property here. What's a property? Well, a property is just a set, right? It's just a subset of some larger universe. In our case, the universe is the set of possible unfoldings. And so the unfolding of W has this property if it's just in this set. Okay, where lambda diamond, is some map which takes a subset of your state space and gives you a subset of the possible unfoldings. And what does it do? Well, it takes some set of states, but this U should be thought of as like a property. It takes a property and it returns all the unfoldings where at least one of the successors satisfies the property. In fact, I'm going to put these little briefs on top of these P's, because this is the contravariant power set. It should be contravariant power set. Because lambda diamond is actually a natural transformation from the contravariant power set to the contravariant power set after our behavior factor. So sorry, I didn't make this explicit, but this B, with B, I just mean this functor here, but this one is very cumbersome to write. So I'm writing B, but it really means this functor in this circumstance. Okay, so this gives us the semantics for the diamond. In fact, and this is something which I think is true, but maybe not everyone. But I think preposition letters are really just nullary modalities, because they can be described in exactly the same way as the diamond, as I do here above for the diamond. Because what you just have is you have this natural transformation from the 0th power of the contravariant power set to the contravariant power set of the B. Really, this is just a subset of possible unfoldings. And which subset? Well, it's those where P occurs as one of the proposition letters that are marked true. And in fact, under this natural transformation, we see that this proposition letter is true at the world if and only if its unfolding is in this set.
Can I ask a quick question, Ezra?
Yes.
So why do I assume, why do we ask sigma of W to be in lambda P instead of W?
So here, okay, so lambda P is some set of possible unfoldings. So W, it's a world, and so we first take its unfolding, and that has two components. So it has a component of, like, it tells you, so it tells you which preposition letters are true there and what are the successors.
Also, sigma is the propositions, is not.
Now sigma is sigma is the coalgebra map. It's the unfolding function for your coalgebra. So W is a world.
Oh, I see.
And sigma of W is then a pair of preposition letters and successor states.
It doesn't make sense. Yeah, I misunderstood the notation. I apologize.
Yeah, sorry. Yeah, I have a lot of, on this slide, there's a lot of implicit notation. So it's, I should have been more explicit about what I meant with things. But, okay. So,
sorry, can you sort of explicate what the where the V is coming from in the second in the lambda P star?
Yes. Okay. So the thing is, so if you look here, the signature of our coalgebras is that you give two pieces of data. So you give a set of proposition letters and a set of successor states. And so if we want to give a set of possible unfoldings, then that will be a set of pairs where the one of the components is a set of letters and the other component is a set of successor states. But of course, in defining this subset, we don't need to use both those pieces of data. So in defining lambda P of star, like, I'm not using V at all, right? It's just, I'm only giving a condition on what A should be.
So is this to say that V can be arbitrary, or V is the whole universe of?
No, V can be arbitrary. So whenever you have some, whenever you have some pair where on the left-hand side you see your proposition letter P, then you say, ah, this is a good unfolding. Here I will accept P as being true.
But does this also suggest that V is all the worlds? Because I'm just trying to work out what it's saying. The V is all the worlds where it essentially works out to be all the worlds where.
Okay, so what I want is so I have my sigma, which goes from W to P of prop times P of W. Right, and now I want to give some condition. When does a world W accept the proposition letter P as true? And that should be if P is in the first component, right, of the unfolding. So I take the unfolding of W, which gives me the proposition letters which are true there and the successors. And now P is said to be true at W if it occurs in the first component of this unfolding. And this is what I'm saying here, right? I'm saying I accept those unfoldings where P is in the first component.
Ezra,
yeah, this makes sense. Yeah.
Also, since you are treating atomic propositions, I mean propositions as corresponding to modalities, which is a very nice thing. I am wondering if here you try to do a modal logic, but not for this particular type of coalgebra, but for, let's say, a kind of polynomial functor constructing on top of power set and something else. Would you define similar kind of modalities for whatever construction you would have in this functor? I mean, here you construct essentially modalities for prop and for the power set. This is what you did, right? In a certain way. And you are using some kind of product construction at a certain point when you are including all these tuples. Why not bring, I don't know, free value modalities or modalities of variety 3 or variety 4 or whatever. I mean, if you present everything as a multimodal logic anyway, why not having
so you can make this more more interesting.
In fact, the nabla operator is a narrative free, and I think is doing exactly this functor of yours, isn't it?
Well,
operator,
I don't want to go into the nabla operator right now.
Okay.
It'll take us too long. But what I'm really all that matters is that we have nullary modalities, right? So any kind of natural transformation of this form will give you a nullary modality, and these are like the directly observable behaviors of your system. And then modalities of higher arities will basically tell you after so many steps we will get the desired behavior. But yeah, I mean, for many different functors you can define like you can get these nullary modalities which will give you maybe precision letters that you find more interesting. But I don't know if this completely answers your question. But...
No, my question was actually for the other, for the higher arity modalities. Then you choose a modality of arity 1 for the power set.
Yeah. I'm
wondering why not choosing also modality of arity 3 for something.
Oh, of arity 3. Well, you can do it. Certainly. In fact, that's my next slide.
Oh, okay. Then, sorry.
So, yeah, so then let's just go to the next slide, because there I just say that you can have n-ary predicate liftings, right? Which is just a natural transformation from the nth power of the contrarian power set functor to this, let's say, set of propositions on possible unfoldings. And so we've seen examples of nullary liftings and the unary lifting before. In fact, in modal logic, you also have a box operator, and that's also given by a unary predicate lifting. Sorry, I was just distracted by the chat. Yes, so where we map a set U or proposition U to the set of those possible unfoldings, where the set of successors is contained in U. So that this means all of the successors satisfy U. So in this way, so this is kind of a very different definition of this box operator. And it's maybe, for me, it's not immediately clear why now box and diamond are duals. That kind of becomes a coincidence, but I don't know. Maybe it's clear to others. But anyway, so this allows you to. So this is another unary predicate lifting. But I mean, to come back to Radu's question, you can also have binary liftings or liftings of even higher rarities. So here's a functor for labeled binary trees. So you mark them with some propositions which are true, and the left successor and the right successor. And then there's a binary modality that lifts two properties to those unfoldings where the left successor satisfies U, if and only if the right successor satisfies V. So, I mean, I have to admit this is a bit of an artificial example, because you could actually also, you could express this modality using just unary liftings for like one for the left successor and one for the right successor, and then using Boolean combinations. But still, I think it looks rather nice. Yes, so this is an example of a binary lifting, and you could have liftings of even higher rarities. You can even have liftings of like infinitary. You can also have infinitary liftings, but then the logic gets ugly because you get infinitary syntax. But you could do it. Anyway, those are liftings, and you can combine those into a logic where you can take negations and like just Booleans really, and modalities given by predicate liftings. And so this is also like you do need some unary liftings in order for this not to be empty. Sort of to get the inductive construction going, you need some unary liftings. But you can have liftings of arbitrary arity also floating around. And so before constructing this logic, you need to specify beforehand some set of predicate liftings that you will be considering. Anyway, so this is our logic, and what's its semantics? Well, the semantics for the Booleans I'm going to skip, but for the modalities, what you do is the interpretation so if we have some coalgebra map sigma, then the interpretation of lambda of phi1 up to phi n in this coalgebra is given by the inverse image along sigma of the lambda of all of these extensions. So what you do is, you first compute this, and this gives you all of the possible unfoldings that satisfy lambda of all of these sort of next step properties. And then you take all of the states such that their unfolding is in here. So their unfolding, so you take the set of states whose unfolding satisfies this lifted property. Okay, that's our semantics, and we get a very nice proposition which tells us that actually along coalgebra morphisms, logical truth is both preserved and reflected. So we have that a state satisfies phi if and only if its image satisfies phi. And this is some, I mean, this is actually some not so difficult diagrammatic reasoning and using some naturality of lambda. But this gives us a very nice corollary that tells us that if two states are behaviorally equivalent, then they are logically equivalent. Because if they are behaviorally equivalent, then we get this span here. And now by the proposition, this state is logically equivalent to this one. And this state is logically equivalent to this one. So these two states are logically equivalent. And so logical equivalence gives us an over approximation of behavioral equivalence. So remember, bisimulation was an under approximation. Logical equivalence is an over approximation of behavioral equivalence. And so as a maybe nice bonus, you can see that, well, if bisimilarity and logical equivalence happen to coincide, then you squeeze behavioral equivalence in the middle, and you see that bisimilarity and behavioral equivalence and logical equivalence all coincide. Okay. I'm just going to take 2 more minutes, I think, to give a specific example where the logic is expressive. So where you do capture exactly behavioral equivalence. And that's in the case of regular languages. So we had this functor for deterministic automata. And this gives us another relifting of acceptance. We say, well, an unfolding is accepting. Well, we already knew that if it in the first coordinate, it says yes, accepting. And for any element of our alphabet, we get a unary lifting. So we lift a property U to those unfoldings where after we make the A transition, the property U holds. And now we get a translation from the finite words over A to our logical language by translating the empty word to just accepting. And if we have some A, then we just translate it to the corresponding modality. And then it's not so hard to see that S accepts a word W if and only if it makes its translation true. Right? S accepts epsilon, the empty word, if and only if it's an accepting state, if and only if it makes the unary modality, the nullary modality acceptance true. And then you just do induction over the words and of the length of the word, and it just works out very nicely. But what does this tell us? This tells us that logical equivalence is strictly stronger than behavioral equivalence, because behavioral equivalence is just having the same language. And now here we see that we can find the language that a state accepts within the set of formulas that it makes true. And so if two states make the same formulas true, they definitely also accept the same words, so they're behaviorally equivalent. And so for this particular functor and this particular set of liftings, we see that that this language is expressive and it correctly distinguishes behaviorally equivalent states. And with that, I want to thank you all for listening.